What if I told you that physics, despite everything it has achieved, is still incomplete? We can predict the motion of planets, simulate the early universe, and describe particles smaller than atoms with extreme precision. And yet, all of physics is built on two frameworks that don't fully agree. On one side is gravity, described by general relativity. It tells us that gravity isn't a force in the traditional sense. Objects move because space-time itself is curved by mass and energy. This theory explains black holes, the expansion of the universe, and even gravitational waves. On the other side is the quantum world, described by quantum mechanics. Here, reality becomes uncertain. Particles don't have definite positions or speeds until they are measured. Instead, everything exists as probabilities. Both theories are incredibly successful, but there's a problem. They don't work together. The conflict appears in extreme conditions, like inside black holes or the very first moments of the universe. In those places, gravity becomes extremely strong and space-time becomes extremely small. That's exactly where quantum effects also become important. But when we try to combine the equations of general relativity and quantum mechanics, they break down. The math stops making physical sense. It's like having two perfect instruction manuals that contradict each other when describing the same situation. This is why physicists believe there must be a deeper framework, a single set of rules that explains everything. This idea is called a theory of everything. Such a theory would unify all four fundamental forces: gravity, electromagnetism, strong nuclear force, weak nuclear force, into one consistent description of nature. We've done this before. Electricity and magnetism were once separate ideas until they were unified into electromagnetism. Later, the weak and electromagnetic forces were combined into the electroweak theory. These breakthroughs became part of the standard model of particle physics. But gravity has resisted all attempts at unification. One leading candidate is string theory, which suggests that all particles are actually tiny vibrating strings. Different vibrations create different particles, like different notes on a cosmic instrument. It even naturally includes gravity. Another idea is loop quantum gravity, which suggests that space-time itself is not continuous, but made of discrete chunks, like atoms of space. But neither approach has been experimentally confirmed. And there's another challenge. Even if a perfect theory exists, it may not be fully usable. Complex systems like weather or turbulence can be described by simple laws, but those laws can be impossible to solve exactly in real life. So even a theory of everything might not let us predict everything. So where does that leave us? We are searching for a single framework that unites the universe at its largest and smallest scales. We don't have it yet. But every step in physics so far, from Newton to Einstein to quantum theory, has been a step toward deeper unification. Maybe the theory of everything won't be the end of physics. Maybe it will be the beginning of a new way of understanding reality itself.